So we'll look at, again, a few complete examples. So the first one is looking at Sizewell C nuclear power station. Now this was built by the UK national company Nuclear Electric, 93-94. It's generating electricity at the moment. It's a pressurized water nuclear reactor. And we'll break down the amounts. Now, all the prices I'm providing here are the original prices from Nuclear Electric. So that's in 1993 prices. Typically, that's 2010 prices divided by 1.6 because of the inflation over the intervening time period. So in terms of construction for a nuclear power station, it takes, well, this particular one took 7 years to build, and that cost £3.45 billion. So actually, when you borrow the money, you're not going to borrow £3.45 million in one amount. You'll borrow it and then spend it over the 7-year period that you're doing the building so that you can minimize the amount you pay back with the discounting rates. If we look at the fuel supply and cost, well, it works out over the 40-year running period for at least the design electricity generating period is 0.3 pence per kilowatt hours in those prices. The fuel disposal, which is a key thing in nuclear, but again, for renewables and other areas is not included, is 0.1 pence per kilowatt hour. The operation and maintenance works out at 0.7 pence per kilowatt hour. The total running costs are therefore, if we just sum these, that gets you 1.1 pence per kilowatt hour. Now, nuclear has substantial decommissioning costs. So the first stage of defueling a nuclear reactor takes about 5 years. And for this reactor, it was costed at 50 million. Removing the outer shield is another 5 years and 160 million. Then the whole site is actually left for 40 years to reduce the levels of radiation. That has a cost of about £1 million per year just to look after the site, do health monitoring, and make sure nobody goes in to any areas that are hazardous. It then is another 10 years of basically going back to a greenfield site, and that's been costed at £190 million. So the total decommissioning and disposal of fuel is £440 million. Now, nuclear has the most extreme of the lifetime of a plant. And I'll show this in the next slide. So you generate electricity for 40 years. At least this is a design time of 40 years of generating electricity. You can see the capital costs for nuclear dominate completely. So almost 70% of the cost of the electricity comes from the capital costs in nuclear. If you look at the expenditure, you can see over the 7 years of build, there's an increase and then it decreases. And then you basically have your operating costs. And these come down substantially because when you stop using fuel, you stop operating. It's the fuel costs that really reduce this quite a lot because the fuel costs and the operational costs are the next 30%. Decommissioning still puts a cost on the electricity, but it's a relatively small percentage compared to all the other areas. But the real problem with nuclear is that you've typically got something like 150 years over the expenditure of the plant. And this is the main reason why it tends to be governments that actually run nuclear power stations, because very few investors and private companies will have people that put money into an investment and will be around in 150 times to get the payback. So you can see here why nuclear ends up having governments predominantly being involved in building nuclear power stations. So for nuclear, the capital cost is always the dominant cost. Now, the other thing we have to look at before you decide on whether to go ahead with building a power station, typically what you'll do is you'll also have a think about what's going to happen if, let's say, inflation rises substantially and the economy does very poorly, as is going on at the moment because of pandemics. What's going to happen to discount rates and inflation from the money that you borrowed? And you'll also look typically at other factors. So the load factor here is really how much electricity you're generating and the capacity factor that it's run at. If you're selling less electricity, you're getting less income, and that increases the cost of the electricity over the lifetime of the plant. But you also look at if there's changes to the capital costs. So that's maybe less important if you know it's going to have a 1 or 2 year construction time compared to a 7-year construction time. But building costs can still increase over 2 years. Fuel costs are the ones that can make the biggest difference for some of these power stations, particularly nuclear with 40 years lifetime. That the cost of the fuel after 40 years, that could change significantly from what you're paying at the start. So you do have to look at how the overall cost of the electricity per kilowatt hour is going to change, depending on all these different parameters and how they may change in the future. Now, of course, some of these parameters can also come down, but typically most of them tend to go up. So this is really looking at the variance of each of these parameters, both going up and down, and you can understand from this what the risks are over the price you can actually sell the electricity to, get payback, and also make a profit. So you can see with this that the numbers we're talking about here, whilst gas is more expensive than nuclear, because gas has 20-year investment and nuclear, well, 40 years for generation, but actually with nuclear, there's another 100 years plus on top of this, simply because of all the other aspects around nuclear. So this is why the combined cycle gas turbine is much easier for private investment. But particularly with the fuel costs, it potentially has much larger risk to fluctuations. Nuclear typically is only viable for governments, as I've said, simply because of the timescales that we're talking about in this. Well, let's go to the opposite extreme now. Nuclear, we had capital costs into many billions. Let's look at wind turbines. And to start with, we're just looking at single wind turbines. But if you're going to build a wind farm, you'll probably buy a number of turbines. We saw with Whiteley's in Glasgow, that's now 240 2 megawatt base plate capacity turbines. Now, if we look at the Siemens 1 megawatt turbines, going back to 2010 prices, they're basically £1,500 per kilowatt hour. Per kilowatt. They have a lifetime of 25 years, and the fuel costs, well, with wind, of course, there's no fuel costs. There's a capacity factor of 30%, and there's an operations and maintenance costs. So one of the things to remember with all renewables is that you still have operations and maintenance costs for the technologies. Now, you might think something like photovoltaics, operation and maintenance is very low. With photovoltaics, one of the biggest issues is actually maintaining the cleanliness of the top of the cells and modules so that you can get dust, you can get dirt. So cleaning costs are really a large part of the operational costs of photovoltaics. With wind turbines, it's a mechanical system. They need a lot of maintenance over the operating period. I should say for wind turbines, both when I started writing this course, but also even now, there's little real data for the complete life cycle of wind turbines of what the real maintenance costs are. So this was estimates from one of the wind turbine manufacturers, Siemens, in 2010. I suspect this is relatively low, compared to what's now known about wind turbine failures. So our capital costs, well, if it's a megawatt, sorry, this is kilowatts, it's 1,000 times 1,500. So the capital cost of the wind turbine is 1.5 million. So this is certainly much more affordable than the gas or the nuclear power stations, but still for most consumers, this is still an awful lot of money. So we look at the annuitized value with 10% discounting, then for every £1,000 we borrow, we're going to pay back £110 per year over the 25-year period. So the annual capital repayment is going to be 1,500 times 110. So it's £165,000 is the annual capital repayment, including 10% discounting rate in this. So that's for inflation, interest, and the time value of money. Now, the annual electricity that's going to be generated, we've got a capacity factor of 30%, and then we're going to multiply by 365 days and 24 hours. If we multiply by 1,000 for we've got 1,000 kilowatts for a megawatt. This is going to give us kilowatt hours, which is what we're interested in for the question. So we end up with 2.63 million kilowatt hours generated by the wind turbine. So now we can start to look at the annuitized capital cost. So we take our £165,000 for the annuitized capital, and we divide by the number of kilowatt hours produced per annum, and we end up with 6.27 pence per kilowatt hour. So you can already see in 2010 prices, just the capital cost of the wind turbine is already greater than the gas and the nuclear that we were looking at. But we still have to add operations and maintenance costs. Now we had the value from Siemens of 1.5 pence per kilowatt hour. So we end up in the earlier, if we compare with the nuclear prices of 1993, and we end up with 7.77 pence, and that's more than double the nuclear prices when we convert to the 1993 prices. So you can see why wind still has government subsidies being put in. I know there's a lot of things in the media that wind is now comparable to nuclear and many other things. Actually, there's still subsidies in wind, as you'll see later in this lecture in the UK. And that's because the real cost of electricity from wind turbines is still more expensive than nuclear. So we price in 1993 cost to compare size, we'll see, we multiply by 1.6. So compared to the numbers I gave before, it's 12.44 pence per kilowatt hour in 2010. So sorry, these numbers were all for 1993 for the wind turbines, and that ends up being 12.44 pence in kilowatt hours in 2010. So one of the first things you get once you've looked at the cost, the payback time, and whether you're going to make a profit from the price you can sell the electricity at, you have to decide whether you're actually going to borrow that money, do the project. So should we invest in the project? And in terms of accountancy, what you do is you work out if the net present value of the whole project, is that greater than zero? And the net present value of the whole project is the net present value from any benefits or income that you could have, minus the net present value of the costs for the whole project. So what we've got here is really, what income are you actually going to get by selling the electricity at whichever price you can get, minus the net present value of all the expenditure of building, running, operating, fuel for the power plant we're talking about. If you can show with the economics that the net present value is greater than zero, then in the investment, you're going to make a profit. Now, actually, the net present value might just be above zero. Your profit could be very small. And with price fluctuations and cost fluctuations, that net present value could easily turn zero, less than zero, and you make a loss from the project. So basically, whilst net present value greater than zero, the project is potentially worth doing. The higher the net present value, the better. The higher the potential profit, and also the less risk of making a loss by making that investment. So the internal rate of return that you hear in accountancy is the discount rate that is required to make the overall net present value equal to zero. So what this really tells you is it worth borrowing money at this discount rate to undertake the project? So you can see here that using net present value that we've defined, you can not just work out the cost of the electricity, you can also work out what's the minimum and the maximum amount to borrow the money at, that you can still make a profit if you undertake the project. So you get what's known as benefit cost ratio. What's the ratio of the net present value for all the benefits to the net present value for all the costs? And projects with benefit cost ratios greater than 1 are worth doing, and the greater the value for that, the better. So this is all general accountancy principles we've been talking about, which is probably why this lecture, I always apologize, it's a bit dry with the accountancy. But this is essential when we look at different forms of energy, because the social aspects of expensive energy are enormous in different countries. So it's key when we look at climate change in the future and how we're going to reduce fossil fuels, how we're going to improve renewables and make much better choices long-term in sustainable energy. At the moment, as you'll see, most renewables and most sustainable energy sources are more expensive than fossil fuels. And this is why they're still heavily used in the majority of the world, and that includes the UK, as you saw with the data in the first lecture. So the UK still is 90% high CO2 from fossil fuels in terms of its energy consumption, and the government's now signed legislation to change that substantially by 2050, but haven't stated how they're going to change that to get to net zero in 2050. So how do governments make consumers like ourselves change what type of energy they're going to consume? Well, this is where subsidies and taxes are used by governments. So why would we use a subsidy and not a tax? Well, subsidies are much better at guaranteeing security of energy supply. They also allow you to alleviate fuel poverty. So you typically will subsidize a high-cost renewable so that poorer people can afford to actually use renewable energy. And that's how you encourage those in the poorer end of society really to get involved with renewable and sustainable energy. It also encourages banks and financial investors to put money into the more expensive but lower CO2 energy technologies. It also, one of the issues that we discussed in the third lecture, one of the problems when you look at biomass is that that has the potential to create famines in different parts of the world, as price fluctuations mean that certain producers, rather than producing food, will produce cheap fuels, and that potentially, if too many of them do it, there's not enough food to actually feed everybody on the planet, and we get famines. So again, subsidies actually reduce this. They ensure food production, and you can guarantee that continuing. It can also, in democracies, be a popular policy that wins you votes. And in democracies, you have to be popular, otherwise you may be out of government. So a lot of the policies that go on are not necessarily the correct policies in government, but they're what's going to get a politician into power and be the government. So why would you tax particular energies? Well, to raise revenue, you can put those taxes and invest it in cleaner forms so that the renewable and the sustainable energies become cheaper. But also, as the UK has done, you can use some of that money to put it into energy saving techniques, so the amount of energy you need to consume in the future reduces. You can raise the effective fuel price, particularly for fossil fuels, and again, that encourages investment to reduce energy consumption and energy conservation. And it discourages consumption, and that reduces pollution and energy imports. Now, for the UK, one of the key things around this is to try and improve the balance of payments. And the balance of payments is quite a key economic issue, certainly for the UK. That will be different in different countries depending where you come from. The other reason you tax people is that you might want to raise money to invest in more worthy or other political interests. Now, the UK is a very good example of this. If you look at the car tax and the fuel taxes that go into petrol, the UK government brings in substantially more money in the taxes than goes back into transportation. And the political argument about this is that they're trying to discourage use of fossil fuels, but also the political interest is to put more money into the healthcare system that actually helps the population, that's much more popular policy with the population, and that wins votes when you go to a general election. So you can see here, these are just some of the examples of why you might choose a subsidy or choose a tax. So here's actually the global energy subsidies from 2012. I'll show in a minute the subsidies for more recent timescales. First time I saw this, when I started this course, I was quite shocked, and I think most students are shocked when they see it. But the point about this is that the majority of subsidies from all the countries in the world are actually given to aid fossil fuel use and make fossil fuels cheaper. So that was a big shock to me. 2012, only 16% of all energy subsidies around the world went in renewable technologies to reduce carbon emissions. So this is all, most subsidies, even to this day, are all about making fossil fuels cheaper to use. So that might be a shock to some. And you'll understand this when you start to look at which countries are involved. So you can see now, and I'm afraid this is a bit of a slide of shame when we talk about climate change, but you can see that there's a number of oil producing countries here that are subsidizing oil and gas quite significantly. Now, I'm not going to make any comments about which countries and regimes and whether democracies are authoritarian or any other political system is better than another. All we're looking at here is which countries are using subsidies to increase carbon emissions. And that's the problem when we look at renewable and sustainable energy for the future. How do we reduce this? Because this is increasing CO2 emissions. And in fact, many of these subsidies, if instead of going to oil and gas, we put these subsidies into renewable or reducing carbon emissions, annually, the amounts correspond to, within 2 or 3 years, you could completely decarbonize almost all energy forms around the whole planet. So the point I'm making here is that the energy subsidies going in oil and gas at present throughout the world could easily allow net zero to happen within a relatively short period of time if there was the political will to do that. But as we all probably understand, many countries do not want to do that for many different reasons. So let's look at the energy subsidies over different years. So here you can see how it's been changing. And actually the energy subsidies are coming down. But they vary over periods of time. There's a little bit of time lag in all this data, because getting some of these numbers, there's quite a bit of lag from some of the countries. But you can look up the International Energy Authority website. That's www.iea.com. And you can download them every year if you want to update the data. This is the data from 1 year ago. So the energy subsidies are predominantly from the oil producing nations subsidizing home oil prices. So the 2010, it was almost 1% of global GDP went into subsidizing oil and gas in oil producing nations. So greater than 400 billion US dollars per annum in 2010. And here are some of the countries named that have been doing this. So removing this subsidy would reduce world CO2 emissions directly by 2 billion tons per annum. That's significant, very significant. And that amount of money is a good significant fraction of the cost to decarbonize the whole global economy. So governments could change this around easily to change the subsidies to improve health, improve education, reduce poverty. Very small percentage of these subsidies go to the poor at the moment. One of the key issues about the climate change agenda at the moment, and part of the reason why things are not being fixed so much more quickly, is that typically short-term additional fuel poverty will particularly affect the poor if many of these subsidies are turned around. So it's not a simple thing to fix. That's the only point I'm making here. It's a very difficult problem to get every country to agree and do it in ways that are considered fair for every country. So let's look at particular subsidy examples, and we're going to look at examples in the UK. So the UK's had the renewable feed-in tariff scheme, and this started in 2012. This basically is for homes. It only works for solar PV, wind turbines, hydroelectric, anaerobic digesters, micro combined heat and power, and only for schemes that are below 5 megawatts. So the point about this is it could be a farmer, it could be a small village doing the investment, it could be people's homes, but it's not for businesses to go out and make a large profit. It's all about generating electricity by renewable means in ways that help save consumption off the national grid. And the idea is to use these renewable and sustainable technologies, power your own home, so you minimize what you're taking off the grid, and then any excess electricity that you produce in your home, or when you're not using the electricity that you're producing, you feed it into the national grid so other people can consume it. There's more renewables actually on the national grid, and you get paid what's known as the feed-in tariff. This is basically a subsidy. So again, this is more complicated when you try and explain it, but when you see the numbers, it's maybe easier to understand how it works. Now, when it started in 2012, these are the numbers that you got. So if you had solar photovoltaic, for every less than 4 kilowatts you generated and put in the national grid, you basically got 43.3 pence per kilowatt hour as your feed-in tariff. If you were doing more than 10 kilowatts, that dropped down to 32.9 pence. So the idea here is that we know the capital cost is greater for smaller installations that you may do in a home compared to a farmer that fills up a much larger field that will be kilowatts, tens of kilowatts rather than 1 or 2 kilowatts. So this is trying to aid and subsidize where the capital cost is higher and the payback time is longer. If we look at hydro, then you can see that the feed-in tariffs, well, it's less than 15 kilowatts and greater than 2 megawatts here, and it's either 20.9 pence or 10.5 pence. And with wind turbines, below 1.5 kilowatts is 36.2 pence, and there's a sliding scale, and it goes down to 4.7 pence when you get above 2 megawatts. So you can see here that what these feed-in tariff numbers tell you is how much more expensive these electricity generating mechanisms are compared to the base load with coal, gas, and nuclear that we have in the UK. Now, in fact, these tariffs have created a lot of controversy because a lot more people invested than the government was hoping. That's a good thing in many ways because it did allow the UK to reduce particularly the number of coal-fired power stations much more quickly than it originally proposed, reduce its CO2 emissions more quickly than it was expecting. But these feed-in tariffs have had to reduce significantly, partly because the technologies got better and cheaper, but also because so many people got involved in them that actually there wasn't enough income from taxing fossil fuels to be able to pay for everything going on here. So it's been a great success in many ways. It's really a subsidy to encourage investment in expensive renewable technologies. It's been a great success in the UK. Many other countries have done similar schemes, and I'm sure other people have got examples they could talk about. Right, so this is a good time for another break and some questions.